found a mind-blowing paper that describes how to outperform your AWS autoscaling group. This technique could save you thousands of dollars and prevent pain, but it's currently only theoretical. In this video, I'll teach you exactly how to build it. Your autoscaling group currently waits for CPU or memory to spike, and then adds servers, but by then your users have already felt some pain. And sometimes, you deploy a new service with extra CPU because you don't trust the autoscaling group to handle a new spike fast enough. This could cost you thousands, even millions of dollars in extra capacity you don't need. So do you think it's possible to be even more efficient with your money? Well, 4 PhD researchers tried to answer this in a paper titled Proactive Random Forest Autoscaler for Microservice Resource Allocation. Kind of a mouthful. Using machine learning, they built a prediction system that can forecast future CPU and memory values required by a microservice. These predictions are then used to proactively adjust resource allocation. By doing this, they achieved a staggering 90% improvement in response time. All of the achievements are based on the random forest technique, and I'll teach you how it works. Random forest is a very popular machine learning technique used by large companies like Netflix, Spotify, and Amazon. It can run classification or regression predictions by creating a large number of individual decision trees and combining their results to produce a final, more accurate result. But before we talk about the forest, we need to understand the tree. You've probably played 20 questions. Your friend thinks of a mystery person, place, or object. You then ask, does it have fur? Is it bigger than a dog? Or does it live in water? Each question you ask splits the possibilities in half. A decision tree does the same thing, except that the questions are about your features and the answer is a number, not an animal. In a single tree, we can attempt to predict the current memory in megabytes. If the CPU is greater than 70, we predict 900 MB. Otherwise, we ask more questions to get more probable answers. That's the basic idea of using a tree. But this tree has a clear flaw. How do you figure out which questions to ask and what numbers to predict? How does this tree learn? And how can it predict your resource usage for autoscaling? Like most forms of machine learning, the tree learns from the data you feed it. Let's say we've recorded our microservice metrics 6 times. On each row, we have the CPU percentage and the corresponding memory value. The obvious pattern is that when there is low CPU, there is low memory and vice versa. It's obvious to you, but the tree has to learn it on its own. One common statistical option is to just take the average. Taking the average doesn't work well though, because averages hide both extremes of the values. But there is a solution, the variance. A high variance means these answers disagree, while a low variance means they are more aligned. Our decision tree can take a look at the variance of the results of each question to determine how to make a prediction. The tree's entire job is to split the data into groups that agree with themselves. Low variance is how a decision can be made. Given our sample of 6 values, let's take a look at a single split. If we ask, is the CPU 50% or less, the table splits into 2. Now, 2 groups of memory values agree with each other. We can measure the variance of these values by taking the mean squared error of the values, as we previously learned when we were talking about linear regression, but instead of subtracting the model's prediction, we subtract the average from the actual value. With the variance obtained, the tree can then compute the gain. The gain measures how much better a split made a node. This is critical for the eventual decision. A tree typically chooses the split with the highest gain because that split reduces the error the most. One final thing to help you understand trees before you use them in autoscaling. How do trees know what splits to try? Where did CPU less than 50% come from? The tree uses a patient brute force method. Most trees can iteratively split on every feature and every threshold. The recursive process ensures that most possibilities can be covered. The stopping criteria then determines when a final decision is made. Some common criteria for stopping are when the gain is getting too small or if you hit a max tree depth. But even after all of this, your tree could still be lying to you. You don't want to deploy a liar to production, right? If we let a single tree grow deep enough, it stops learning and just starts memorizing. Tree nodes will be created for every fluke and every random dip in your training data. It just learns from noise that will never happen again. So your tree then looks like a genius on the data it studied and a complete fool on anything new. In ML, this is called overfitting. So what can we do to our tree to make it more accurate for predictive autoscaling? Well, we plant multiple trees to make a forest. If I hand you a jar of jelly beans and ask you to guess how many, your answer is most likely way off. But if I ask 1,000 people and average their guesses, the answer is likely to be pretty close. The high guesses and the low guesses cancel each other out. The random forest technique does this with decision trees. The average of lots of mediocre different trees is better than one perfectly tuned tree. But there's a catch. The guessers have to be independent. If everyone copies their neighbor, averaging does nothing. So a forest forces its trees to be different with two types of randomness. The first type of randomness is known as bootstrap aggregation, also known as bagging. Instead of training all trees on the same data set, the algorithm creates random subsets of data for each tree. Every tree learns a different part of history. The second piece of randomness is random feature selection. At each split point, the decision tree can only look at a random subset of features. This stops every tree from leaning on the obvious feature and asking the same first question. The result of these techniques is that trees can disagree in independent ways, and when you average disagreeing but independent guesses, the errors cancel. So now that we fully understand how the random forest technique works, let's implement it in a couple of lines of Python. The first thing we will do is write a single tree. So I have a couple of helper functions here that will be very useful in actually implementing the tree. Just know that in this video, my goal is to teach you what is possible. I'm not really focusing on like memorizing any of how the code works because scikit-learn and some other statistical packages already implement some of these things for you. But it will be useful for you to understand how things work by implementing it from scratch. So let's go. The first thing we're going to do is implement the tree. So in terms of implementing the tree, because it's recursive, the first thing we need to actually look at is implementing the first stopping criteria, which is if your max depth has been reached, then there is no need to proceed since it's a recursive function. If you've implemented recursion before, you would understand this pattern. So if we need to stop and say, have we reached our max depth? Then we return a leaf. And the value of this leaf is the mean of our y parameters. In the context of a tree, you can either have a node or a leaf. So a node can have either a child that is a node itself, that is another node, or a leaf. And in this case, a leaf just means the end of that branch of the tree. So we return a leaf if our stopping criteria is met. The second bit is, now we need to do feature selection, select our threshold, split the nodes, and calculate the variance. It's a bit chunky, but this is where most of the work is. So for every feature, right, in our random feature subsets, because we're doing random feature selection, we also need to select our thresholds, which of course I have another helper function for that. And our thresholds come from the list of features we have, which is X. So we selected our thresholds and then we can do our left and right splits, which is given by our X features, Y values, of selected features, the random features, and our given thresholds. Based on these features, we can then calculate the variance and calculate the reduction of the variance, which will help us determine the gain. So, given our variance reduction based on the split values, we say if our best, I forgot to initiate our best variable. This is just the best splits variable, which you'll see soon. So if our best is none, or our gain in this case is greater than our best gain, Then our best split then becomes this given the feature we selected, the threshold and the gain, right? So this is what we iteratively or recursively compare against. The last thing we need to do before returning the next node is we need to calculate if we've hit another stopping criteria, which means have we hit the best gain we want. So if our best gain is less than the minimum gain we've set arbitrarily, in this case, we return another leaf. So the value is the mean of this, right? So the next thing is to do another split. Why we need to do this will become apparent soon. We need this split because we're returning a final node, and this node now includes our current best, but then we're also trying to split, so we build two new trees. So we build a tree for the left side and build another tree for the right side. So we do a depth plus one, that is it, and then build another tree for the right side. So let's build another tree, which will be right.x and right.y. It's fun to write code by hand. And then add to the depth. So that's it, we built the tree that can be used recursively. One neat thing will be to then see how you can use this tree to predict, right? So for that, there is this simple helper function that shows how to predict the tree. So what this helper function does is until we get a leaf, we just continue recursively working the tree. And when we get a leaf, we return it. That's literally it. So now that we built the tree, we can do the forest, right? So the forest is like ironically easier because all you need to do is accumulate trees, run predictions on the trees, and calculate the average to do your prediction. First of all, we'll write a function to train the forest. In this function, we're specifying the number of trees we want, which is j, the sample size, and the max number of features. That will become like apparent soon why we need to do that. So the first thing we need to do when building the forest is initialize a list of trees, an empty list, and then for the range of trees we want, right? Because we need to create a tree for every j, for the number of j we want. We do bootstrap aggregation, which we mentioned in the earlier part of the video, where we select random features. We select random samples of the data we have with replacement. So that's what this helper function does. And then we pass in the sample size we want. So for each of these, we just append a new tree, right? By building a tree based on the values we've selected. So the max number of features that goes in is determined by what our function gets. And we've created our trees because we can build trees. So all we need to do now is just return the trees we've created. And that's it. That's how to train the forest. Now that we've trained the forest, we can now use that forest to do some prediction, right? This bit is also very straightforward because what we need is a list of trees that we can run predictions on, and then we get the mean of those values. Given a list, we can run predict tree for all the trees for tree in trees, and then return the mean. This converts to a numpy array, so numpy can do the nice prediction for us. And that's it. We've predicted our forest, we've predicted our tree, and we're done. We've come full circle. For making it this far, I'll give you the keys to add this to your autoscaler implementation. For each service, we grab 6 metrics. We then use these features to predict CPU and memory for the next window. This loop can run forever. Monitor, analyze, plan, and execute. In the paper, the researchers split the autoscaling decisions. CPU is scaled horizontally, while memory is scaled vertically. This is a genius move, since the CPU is often fixed, while ohm kills cannot be fixed by just adding more replicas. They also state that vertical scaling is given priority over horizontal scaling to avoid out-of-memory errors, since a container is terminated if it exceeds its memory limit, unlike CPU, where you can tolerate some higher utilization at the cost of some extra latency or response time. The wins from implementing this are obviously enormous. In the experiment, the researchers found that tail latency drops by almost 20 times, up to a 95% improvement, which is mind-blowing. They also noticed that out-of-memory or errors were nearly eliminated, which is one of the most important takeaways for customers. No more random failures. Another big win is resource efficiency. By only provisioning capacity that is actually needed, a lot of money is saved, which starts to add up in the yearly balance sheets. Overall, this is proof that tree ensembles or the random forest are perfect for prediction in the messy world of infrastructure that we operate in. So let's recap. In this video, you've learned how to beat your reactive AWS autoscaling group. You've learned that a decision tree is simply an ML game of 20 questions that returns a single number, not an animal. You've also learned that a single tree suffers from overfitting and memorizes noise, so we can use a forest. Then you learned that a forest grows many trees and averages their results, which cancels their individual mistakes. Finally, you learned how we can apply this to predict CPU and memory and feed it to an autoscaler MAPE loop. If you're excited about topics like this, make sure to subscribe for more in the future, and see you in the next one.